Welcome back. We're going to take a little bit of a detour from what we've been talking about so far and introduce the concept of low-rank matrix approximation. This actually has application in total least squares, which is something we'll touch on briefly as well, but also in sparse coding and sparse signal analysis. So we'll start by setting up the problem with A being an M by N matrix, and it has rank capital R. So often the question we are trying to come up with is we want a matrix, and I'll just say X, of rank R less than R that is closest to A. In other words, we want to minimize by choosing X. A minus X squared, and we'll look at use the Frobenius norm here, subject to rank X is equal to R. And just as a reminder, choose some of the matrix. W Frobenius norm is equal to the sum over rows and columns of W comma N squared. So it's just the square of all the elements summed up. Okay, so the first part is easy, this minimization. We're used to doing problems like that. But the second part, subject to rank X equals R, complicates things a bit. So, first, some concepts about low rank approximation. This is a good time to bring all of this up because we've been using the singular value decomposition seemingly for almost everything. Very valuable tool. And it's been successful so far, so let's try it again. Let A be a matrix with SVD A equals U sigma V transpose, and we know we can write this in terms of what we sometimes call the spectral decomposition, although that term applies to both expressions, where it's a sum of rank 1 matrices, the outer products of U and V, scaled by the SVD. Well, if we call that equation 1, then 1 is solved by simply truncating the SVD. So X hat that solves this problem, that minimizes equation 1, is P equals 1 to R, sigma P, UP, VP transpose, and we'll just denote that by UR sigma R ER transpose, where these terms here contain the first R columns of U and V respectively, and the first are rows and columns of sigma. So in the PDF notes there's actually a proof of this, and it's more than I want to go into right now. It's quite a lengthy proof, but I think it's easy to see maybe intuitively what's going on here. If X is made up of, let's go back to, if A is made up of a sum of rank 1 matrices like this, and each is scaled by the singular values, then it makes intuitive sense that if you get rid of the last one, where the singular value is the smallest, it's going to have the least impact on matrix A. And so if you want to approximate A with a lower rank matrix, you would approximate A with itself sans these insignificant smaller terms at the end of our singular value decomposition of these rank 1 matrices that are scaled by the smallest singular value. So once we've done this, what is the error here? Well, let's take a look. We know now that A minus X bar is just equal to the sum of the singular value times their respective rank 1 matrices that we left off before. So U, P, V, P transpose from the ones that we truncated. Well, what's the norm of this? The Frobenius norm squared of A minus X hat is just going to be equal to the sum R plus 1 to R sigma P squared. So if you need to approximate something with a lower rank, we just get rid of the parts of the smallest parts of the singular value decomposition. And this harkens back also to when we were solving least squares problems, and we used our singular value decomposition, and we found that, hey, if we wanted something that didn't cause the error to blow up, we were better off just getting rid of the smallest terms, because it had a small impact on the modeling error, but a large impact on reducing the noise.